Anybody? Some of you said you did it.
Yeah.
How? Step one, make an acetal to protect what? And what are you using to make an acetal?
Like a dial.
Right. So remember, we want to try and make a 5-membered ring or a 6-membered ring. That's carbon 1. So we need 4 more atoms or 5 more atoms. 2 of those are, of course, oxygens. So you can either diol, or that'll be your 5-membered ring, or you can use this diol, which will give you a 6-membered ring. So that's either of those is okay, but it has to be in presence of
An acid.
catalyst. Exactly. Okay, then what so we protected this. Then what? Grignard, what? How much?
I'm sorry, I'm just reading the way I wrote it too.
That's okay. I'm sorry, could you say that one more time?
Excess of ethyl and BGR.
Why? Why excess?
Because
Exactly. Esters. Remember that esters and acid halides react with 2 equivalents minimum of Grignard. So you at least have to have 2 or excess. Otherwise, it's not a good way. It won't work. So does everybody remember that? Everybody? Okay. And then what? So that will convert this into the acetal still remains intact, because acetal does not react under basic or acidic conditions, but this creates the mechanism you should know. It's the mechanism you should know for this, you should know the mechanism for this, and then what?
the oxygen gets protonated.
No, so what are you using?
Oh, there
Because again, the mechanism you should know. We're not writing mechanism, no, we're just writing sentences. Yeah, does everybody, is that what everybody got? Yes, ma'am.
Writing like the dilute acid, so you need it for the oxygen negative charge and to reverse the.
Everything.
Do you
Right.
need to put excess? Or
Of what? That's a good question. Excess of what?
I think it's the dilute acid.
What does dilute acid mean?
water.
Yeah.
What's the role of the H plus in that step? Again, you got to think of the mechanism. Protonating, but then eventually what? If you think of the mechanism of the acid, what is it reacting as?
Catalyst?
It is a catalyst. So if it's a catalyst, it's being used and produced, used and produced, used and produced. Do you need an excess?
No.
Catalyst, you never need more, because again, that's the thing, right? It recycles itself, at least theoretically. Now, here's the practical aspect of it. Whose excess do we really need? Water. But if you're going to have dilute acid, isn't water already in excess? Does that make sense?
Yeah.
So practically speaking, I mean, it's already excess water. It's lots of water, because you said dilute acid. Make sense, everyone? Is this what everybody kind of sort of got? And was there just one? Okay.
Yeah, there were just mechanisms, but
Okay.
normal.
Normal.
Like,
Okay, I don't remember the number. Reaction number is, can someone tell me what the reaction number we were at, the last one?
That was reaction number 3.
3? Okay, so let's get to 4 then. Reaction of aldehydes and ketones is what we are discussing right now. So reaction number 4, which is actually very, very similar to acetals and all, because these are making thioacetals. Thio refers to sulfur, by the way. Thiols are alcohols with sulfur instead of oxygens. Thioketones are ketones, but instead of oxygen you have sulfur, so on and so forth. Thioesters and blah, blah, blah. Thio is indicating sulfur instead of oxygen. That's what it means. Okay, so this one we've seen before. We're just looking at it again. If you have an aldehyde or a ketone and we react it with, just like instead of a diol, if I reacted with a dithiol in presence of a catalyst, acid catalyst, what would that create? Anybody?
a thio
thioacetal. In this case, it
Thioacetal.
would be a cyclic one, right?
Yep.
And what size ring would it be? So again, carbon 1, 2, 3, 4, 5, 6.
Six-membered ring.
Six-membered ring. Everybody agrees?
Mhm.
Everybody okay? Now, we saw this before, and that was specifically for aldehydes. We saw this, right? Where you can use butyl lithium that gets deprotonated, becomes a nucleophile. You can do SN2 and then convert aldehyde into a ketone. We've already seen that reaction. Just FYI, the thioacetals can be converted back into the parent ketone or aldehyde also with dilute acid, just like acetals. But there is one other reaction that thioacetals help us do. One that we've already seen before, I'll just write it here. Once you get that, butyl lithium, and then R prime X do an SN2 reaction, and then H3O plus converts an aldehyde into a ketone. We already saw that, right? We've already seen that reaction before. But there's one other thing they can do, which is if you treat it with something called Raney nickel. It's basically nickel metal with certain groups on it to control the reactivity of nickel itself as a catalyst. It basically converts the aldehyde or ketone, whatever that is, into an alkane. So the C double bond O becomes, please notice from the beginning, the C double bond O becomes CH2.
I'm sorry, what was running?
Raney nickel is something called, basically it's nickel with certain groups which we are not getting into to control the reactivity of the nickel. That serves as a catalyst. It's called Raney nickel. Okay, so again, in terms of mechanism, we should just be able to write this mechanism and this mechanism. Those mechanisms we don't need to know. And these mechanisms are exactly like the mechanisms for acetal. Making an acetal or hydrolyzing an acetal, exactly the same mechanism. Does that sound okay? Mm-hmm. Yes? Okay. Let's just look at a couple of examples to get an idea. So for example, that's supposed to be a 3. It's a U. Sorry, that looks like an A. It's a U. Okay, please feel free to go write the answers up quickly.
Carboxylic acid.
Hmm? Oh.
Oh,
Didn't think about it.
next one. Are you groaning because they're making you get up?
What, actually, maybe for somebody else?
You're good, you're good.
You're good, you're there, Nure. Do you all agree? Yeah, because
Okay.
that portion comes from the aldehyde, and then this portion comes from SN2 step.
Mhm.
Cool. Questions? Okay, the next couple of reactions of aldehydes, ketones we've seen before. They're not new. We are just formally just including them in the list of reactions of aldehydes and ketones, but we've seen them before. So hopefully they're extremely familiar to us. So reaction number 5, reduction of aldehydes and ketones. Aldehydes and ketones can be reduced. Does anybody remember what reagents to use to reduce an aldehyde or a ketone?
An oxidizing agent?
Well, if you're reducing, why would you use an oxidizing agent? La is
La.
one. What
La.
else?
BH3.
Not
NABH4?
BH3. Sorry?
NABH4?
Sodium borohydride.
Oh.
So the two reagents used to reduce aldehydes and ketones is either sodium borohydride or La. Now, what does La stand for again?
Lithium aluminum
Aluminum.
hydride.
And
Four.
if you are using sodium borohydride, what is it used with, generally speaking? What do we use?
Methanol.
Generally, methanol, ethanol as the solvent. And what about La? Do we use the same for La?
No.
No. What do we do instead? That's a two-step process because La, being a very strong reducing agent, should be not used without anything protic, so we have to bring a protic source later on as a separate step. Does everybody remember that?
Yes.
We also wrote a mechanism, but what would be the product?
Oh.
If an aldehyde or a ketone is reduced with sodium borohydride or La, what's the outcome?
An alcohol.
An alcohol. Alcohol. What kind of alcohol does a aldehyde produce?
A primary.
Sorry, I lost track of where I was. Primary, and if it were a ketone, what kind of alcohol would it be?
Secondary.
Okay, cool. So let's do this a couple of times just to remember. And mechanism, we did write a mechanism for this also last quarter, so we should be able to do so. please tell me what is the product, what are the products here? Emma? Done?
Ketone.
Gonna tell me what the product would be? Okay. Cyclopentanol for the first one, do you all agree?
Yes.
And the
Okay,
second
let's-
one would be
Let's, what would it be?
phenol.
No, not phenol. You lost a carbon.
Oh, okay.
What would it be? Anybody?
A second,
What would the product be? Benzyl alcohol.
benzyl
Absolutely.
alcohol.
Benzyl alcohol is of course not an IUPAC name. That would be phenylmethanol, but let's quickly write a mechanism, at least one, so you remember the mechanism. Can someone tell me what's the first step?
Hydride comes.
From where?
Hydride from the NABH.
Which part of NABH4 gives us the hydride?
One of the H.
So not the sodium ion, that's just a counter
Yeah.
ion. It's the borohydride, which is a source of a hydride anion. Isn't that right? It's electron rich. It wants to get back to its neutral state. And the only way it can do so is by donating a hydride. Where will that hydride go?
On the oxygen? No.
Is that electron rich, electron poor?
Rich.
Is hydride electron rich, electron, then why should rich go to
Electrophilic
rich?
carbon?
So hydride acts as a nucleophile, attacks the electrophilic carbon. Right? What does that create in this case?
O minus.
Becomes
Alcox.
Alcoxide.
alkoxide, O minus, and then what does this guy need to do?
Deprotonated.
And where is the deep? Did you say
B.
deprotonate?
No,
Deprotonate. Sorry.
deprotonated.
I heard depro. And where is the proton going to come from?
From the alcohol.
In this case, that's coming from methanol, giving us the proton to give us the product. And it's the same with La. The mechanism is the same. It's just that the hydride is coming from aluminum hydride, but the mechanism is the same. Do you guys remember this? Next reaction, also we've seen before. In fact, we saw it last quarter, but we also did it this quarter as well. And it's exactly the same as this in terms of the mechanism, and that is reacting with a Grignard. Right? We've seen that aldehydes and ketones react with Grignards. Can someone tell me what is the outcome when we react with Grignard?
Attach.
With
Two new arbor.
why two?
Oh, just one, sorry.
This doesn't have a leaving group, right? Bad leaving group, bad leaving group. That's for esters and acetyl halides that do have a leaving group. So what will this give us? It will give us an alcohol, but with an added R, right? You're adding carbons. So we've seen this also several times this quarter as well as last quarter. So, and you should know the mechanism, you should be able to write a mechanism, guys. Please tell me what is the product. And by the way, how many equivalents of Grignard needed for this reaction? Just one.
Just
exactly.
one.
Because Grignard is reacting only once. So what will the product be? And let's write a mechanism. Exactly the same mechanism as the reduction reaction. The only difference is the nucleophile.
You want us to write?
Yeah? Okay, since you're there, why don't you write the mechanism too? Unless you don't want to. That's- Do you all agree with the products? Yes?
Yep.
Yep.
And then, of course, the mechanism. Nucleophile attacks the electrophilic carbon of the C double bond O, creates an alkoxide because there's no leaving group. And so the alkoxide gets protonated, becomes a perfect. Does that sound okay, everybody? Questions?
Yeah, well, that's just normal.
Yeah, exactly.
I mean, no,
Exactly.
I don't see anything.
Yep. I like it when you start calling these mechanisms normal. It's like, oh, that's so cool. Now this is normal. Great. Okay. Just trying to wait. Ooh, you lost the. No, you didn't. Ooh, one thing I won't do, Dash, is make an anion. There's no anion. There is. This just goes directly. So it's not that it breaks up first and you've got anion, free floating anion, which then goes attacks. It's a
Okay.
simultaneous process. Yeah. Perfect. You can just point it to the product if you want, but yeah, absolutely. Okay, the next reaction that we are going to talk about, again, please notice the mechanisms are so similar from one reaction to the other. It's the same sequence of events over and over again. The only difference is the nucleophile changes, right? If the nucleophile is this, you get that. If the nucleophile is that, you get this, blah, blah, blah. Everything else is kind of the same. So the next reaction is reaction with a primary amine to create an imine. Imine is created when aldehydes and ketones react with primary amines. Does anybody remember what's a primary amine?
An amine, a terminal carbon.
So, doesn't have to be, by the way, a primary amine doesn't have to be at a terminal carbon. Does anybody remember what's a primary?
Would that
amine?
be N and 2H?
Exactly. Now it can be in the middle of the chain too,
Yeah, NH2.
but you're right, it is one that has two hydrogens on the nitrogens, that's primary amine. Secondary amine, just to remind everybody, this is for amines. That's where amines are different from alcohols. How you decide whether an alcohol is primary or secondary or tertiary is based on the carbon the alcohol is attached to. But for amines, it's based on the nitrogen.
Oh.
So yes, And secondary amine is where the nitrogen is connected to two R's, one hydrogen. Tertiary is no H's, just R's. And there is also quaternary, although that is not neutral. That will become a cation, ammonium. That's a quaternary ammonium ion. But coming back to the reaction though, aldehydes and ketones react with primary amines to create imines and water. So if you have an aldehyde or a ketone, react with primary amine in presence of an acid catalyst to create an imine and water. With that information, can you guess what an imine is? The byproduct is water. Can you guess what imine is? You're saying swap the O and the N?
Yeah, in one
With what kind of bond between
One bond.
them? Well, if it's one bond, then shouldn't somewhere
Well,
there
I mean-
should be a charge?
let's see, N, and then there's another R. We should add another R.
No,
No,
fine.
no, okay.
So think about it, guys. The byproduct is water. Where is water coming from?
H2,
H2O, right? So you're in a way you're correct that let's just swap the nitrogen and oxygen. But what kind of bond between the nitrogen and the oxygen? Exactly. Can't be a single bond because then you will have charges
yeah.
somewhere. That's an imine. It's also called a shift space. In biochem, they don't call it imine, they call it a shift space. But again, who cares? You can call an apple Timbuktu, it's still an apple, right? Shift space. So in case you come across that term, which you will if you do biochem, please remember. I'm laughing because who's going to remember them like 2 years from now? But if you can, it's just an amine. It's nothing more. Okay, let's look at an example. Write a mechanism. Where's my cheat sheet? Fine. Why do I need a cheat sheet? Okay, fine. Let's do this. Please tell me what's the product.
Just product.
Yeah, for now. Then we write the stepwise mechanism. Yeah, what would the product be?
Swap the O at the end, then put a female at the end, keeping the double bond.
Last page. Agreed? Everybody? Okay, let's try and write a mechanism step by step. What do you think is the first step of this process?
The phenol goes into,
The phenol,
no,
Phenyl goes nowhere.
no, hold on.
The oxygen is coordinated.
Say again?
The oxygen is coordinated.
Exactly. If remember, when we were discussing
Oh,
the
yeah.
general sequence of events, if there's an acid, the first thing you do is protonate the
Sure.
oxygen. Protonate the oxygen. Okay, so if that gets protonated, then what? Once the oxygen
Then
gets
we-
protonated,
We have a positive.
okay, yeah, but then what? What's
Um,
next step? What happens in generally speaking, once the oxygen gets protonated, what's the next step that comes after that?
the double bond.
No. The,
Guys, we talked about the general sequence of steps in all of these mechanisms, right? If there is an acid, if there is no acid, nucleophile attacks the electrophilic carbon and then the O gets protonated. If there is an acid, oxygen gets protonated first and then what?
The nucleophile comes in.
What's the nucleophile here? So the amine, the primary amine is the nucleophile. In this case, aniline, and Where? From where? The nitrogen. Why? Because it has a lone pair. Isn't that right? That's the same sequence of events, guys. We are not really changing any of those yet. Okay, so the nucleophile attacks the electrophile, creates a tetrahedral intermediate. Okay, what do you think should happen next? Guys, I need you to be able to recognize the patterns here. What am I missing?
There's a plus that
Where?
in the end, not nitrogen.
Where?
In the end,
On
Where?
the end.
In the end, where? On which atom?
on top,
On the
Which
nitrogen.
atom?
nitrogen.
Oh, I didn't hear that part.
Oh,
Absolutely.
I'm like,
It's on the nitrogen. I'm like, where? Which? Exactly. Now what? What would you predict happen next?
well, we need to deprotonate it?
Okay, you need to deprotonate it.
Will the
Okay,
oxygen take?
but not from the same. Meaning there'll be two separate steps. One step where this deprotonates, another step where that gets protonated.
Okay.
It's called proton exchange. It's basically can't be intramolecular. The transition state isn't big enough. For intramolecular processes, transition state of 5 or 6 is good. Anything other than that is not. So the point is, yes, you're recognizing that somehow this has to get rid of a proton and this has to get a proton, so it becomes a leaving group.
Mm-hmm.
Everybody's recognizing it? Just not in the same step. It's not this taking a proton. That's wrong.
No.
Because it's not intramolecular. It has to be intermolecular. Now, how do you show it? Again, there are different ways. People have their own versions. One option is, let's just do it one step at a time. Let's do that first. And then show that getting protonated again. Sure, totally fine. You can do that. Or, here's another way sometimes people show it, so that's going, and I will just have a proton here. This is take proton, you just go directly here. Either way, it's a matter of choice. The only thing is, you need to make sure that you're showing this as in two intermolecular processes, not an intramolecular process. Yes?
Well, Vincent and I were wondering, where does the H go? It just breaks, just where does it go? Like,
Are we just taking one proton in this entire system?
Huh?
Oh, where does the proton go? Is that what you
yes,
said?
in this,
Where
in
do you
this
think-
one here. Like when
So-
you break it and it just, the red,
This one?
there. Mhm.
Yeah, so did I just use H plus?
Yes,
Practically speaking, no, you gotta be practical here.
yeah.
Do I have bottle of H plus?
No.
Do we have bottles of protons sitting?
No.
What do we actually have?
Acids.
Oh, okay, yeah, that's what that means, but what do I actually have?
Water.
You have hydronium, isn't it? Isn't H plus the same as hydronium?
Yep.
Or maybe it's HCl, maybe it's TSOH, maybe it's whatever. The point is there always something with H plus?
Yes.
Can that something come and take the proton? We have to actually show it. It's a choice. It's a matter of choice of how you prefer to write
Okay.
it. I wrote H plus because I had H plus there, right? So I took an H plus, so I'm giving away an H plus. But if it were H3O plus, then there's water. If it were HCl, there's Cl minus, so on and so forth. Does
Got
that
it.
answer your question?
Definitely, yeah, that's what I
So-
thought, but I want to make sure.
Exactly. So those are all those things that are happening in there when the reaction is taking place. So please, whether you show step by step or you just show this gives a proton, that takes a proton and go directly here, totally okay. Questions so far? Say again?
Hydronium is catalyst.
H plus is catalyst. Yes. Yes, exactly. It should be. In this case, it is.
Did you say
catalyst.
that we could show it in one, of course, they're different, but in one step we could show like
Yeah,
that?
you can either
Oh,
show
okay.
this or you can show this.
Okay,
This is giving a proton, that's taking a proton, directly comes here.
yep,
Yep.
okay.
So, what's next though? So ultimately we get to this point.
Leaving group leaves.
Leaving group. You got a great leaving group. Why is that? Sorry. When that leaving group leaves, what will it create?
Water.
Don't care. What about the organic stuff? Carbocation. Have we seen this kind of a carbocation before?
Yes.
Please, yes.
Never in my life.
Yep.
What's so special about this carbocation?
Resonance.
From where?
The nitrogen.
You did it with oxygen. Well, it's the same thing. This has lone pairs too. Why can't that do it? Same thing. It is a resonance stabilized carbocation coming from the lone pairs which we've seen before, right?
Mhm.
So what would you expect to happen next?
Losing the proton, or something takes the proton. Like
From
the-
where?
From the nitrogen.
So since I'm just doing H plus all around, I'm just going to do H plus, but yeah, you're right, something's gonna come and take that proton, recreate the catalyst, give us the shift space, the imine, and the catalyst. Again, please, instead of looking at specific mechanism, do you see the trends, the patterns? The mechanism is exactly the same as acetal mechanism, because you're protonating that first, and then the nucleophile is attacking, and then the OH is getting protonated, so it becomes a good leaving group, makes a resonance stabilized carbocation, blah, 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 same thing. Agreed? Everybody okay? Questions? Is it really catalytic in protons? Let's make sure. Used one, created. Okay, so that's balance. Used one, created. Perfect. So it's catalytic in H plus as well.
Mhm.
Everybody okay?
Yes.
Questions? You want to write it one more time?
Mhm.
No,
We're
did I
good.
get it? No?
I'm good at, but I don't know. Everybody else?
Oh, Mar is saying you're good?
Yeah.
You got it? Okay, cool. Then we don't. Okay, fine. Is that okay with everybody? Or is Mar the spokesperson for everybody today? Okay, fine. Let's do a couple more examples though. You can practice writing mechanisms at home.
Well, unless there was like one that's intra or something. No, but it's the same. Never. Or something tricky that we could go over. Like in an exam.
You said tricky?
Yeah. Give us the trickiest one.
Trickiest? No, there's no such thing as trickiest. It can get tricky as much as you want.
Yes, that's good.
Okay, it's not tricky really, but. Can it happen intramolecularly? Here is an intermolecular reaction. One molecule brings the C double bond O, the other one brings the primary amine. But can it happen within the same molecule?
Yeah.
Absolutely. As long as the new ring, what sizes are desired for the new ring?
5 or 6.
5 or a 6 membered. Then it can.
You go bigger than that, or just 5 and 6?
5 or 6 is the preferred ring size because those are the most stable rings of all the cyclic structures. So, while you guys are working on that, Did you lose? Those reactions over there are actually some diagnostic tests we do to ascertain if there is an aldehyde or a ketone in a compound. So we don't do this anymore. We used to do a lab that ran for 4 weeks of the quarter where I would just give you, tell me what this is. Literally, here is something, tell me what it is. So you got to do some diagnostic tests to figure out what are the functional groups. Is it an alcohol or an aldehyde, ketone, blah, blah, blah. So these are some diagnostic tests that are done to make sure, to ensure that there is an aldehyde or a ketone in a molecule. But it's really nothing but that. It's the same reaction, but that's the purpose those are used for.
Is this one correct?
If not, you draw yours. We'll see. Why do you think that's not correct?
Miss,
Yeah?
I have a question.
Yes.
So, in the textbook,
Yes.
the mechanism,
Yeah. They did that first. I was noticing that too. It doesn't acid, so I think we should just protonate first and then go. Yeah, I was
but would
noticing.
it be wrong?
This reaction is specifically for primary amines. Something to also think about. An amine. More?
Now I remember.
What about that board? Nobody else wants to go? It's Ali's coming. Yeah, please go. Yeah, great. Dash. Ali was going to do that one.
No, it's okay.
It's fair game.
Okay, no. Now she
You're
sat
good.
back down. Okay. Next time, Ali. What about the other one? No? Not yet for that one? I don't know what that is, but okay.
Yeah. Any takers?
Ooh, carbon with 5 bonds. Careful, careful. You lost a carbon. There we go. So my kindergarten through 8th grade, this is like way back when, I went to a Catholic school, with fathers and nuns, sisters and everything, the whole shebang. And I remember one of our principal, she wasn't, Sister Mercedes was middle school, whatever, one of the sisters. So, in grammar, they used to be very particular about grammar. And that's why I think my grammar is way better than my kids and all. But that's something I always remember. Let's say if we were saying, if Carter and I were together and I said, I and Carter went blah, 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 she would smack you and say, me the donkey first. Always stuck in my head. Oh, there was plenty of smacking back then with rulers. But that always stuck in my head that, I always go in the second place. The other person always, so it's always Carter and I and not I and Carter. Mm-hmm. But now I see everybody mixing in, and I cringe on the inside because Sister Mercedes is constantly speaking in my head. Similarly, there was a chemistry relationship here. Carbon with 5 bonds. If I see carbon with 5 bonds, again, it's very cringy. No, please, don't do carbon. So hopefully that'll stick in your head 10 years down the road. Sumita, carbon with 5 bonds. Although I'm not smacking you, but. Perfect. Okay, let's look at them. Do you all agree with these two? Agreed? Yes? Yep. Perfect. How about, that's again, FII. That's called hydroxylamine, so this is an oxime. Who cares? What is that? Hydrazine, so this is called a hydrazone. Mm-hmm. Okay. This is called 2,4-DNP, 2,4-dinitrophenylhydrazine. So the product is a 2,4-dinitrophenylhydrazone. Do you all agree with the products? I don't agree with that one. Which one? This one. Why? The reaction is for primary amines. Amines. Is this an amine?
No.
What is it?
An amide.
An amide.
Look at the other side.
Yes. That is the amine.
Oh.
This is the amide. So that would not be correct. It's for primary amines. So
There was a tricky
it
one.
would have to react from the other end because these are amides, those nitrogens. Do you guys see the difference? Yeah. Okay. What about here? Do we agree with, so again, this portion comes from the ketone and then this comes from the primary amine. Looks good. Again, that's the aldehyde part because there's a hydrogen here and then hydrazine. Perfect. Do we all get it?
Yes.
Everybody good? Cool. Now, amines, let's take one. How about we use this as an example? Because you've seen this also plenty of times now, so hopefully you can tell me. What's the byproduct?
Water.
Water. Again, we've seen this so many times now. This reaction is reversible. What would I need in order to make the amine go back to the aldehyde ketone and the primary amine?
Water.
In presence of, absolutely, in presence of the catalyst. You need catalyst for both sides. You need a catalyst to go this direction, you need the same catalyst to go in the other direction too, but you're absolutely right. If I had a dilute acid, I can just go back. Everybody sees that?
Mm-hmm.
Yes, let's do that a couple of times. Again, mechanism writing, absolutely, to make sure you understand the process. Okay, so please tell tell me. Already did that one. So what should I use if I'm going in the reverse direction?
Water.
Hydrogen.
So water with acid or hydronium, dilute acid, whatever you want to call it, they all mean the exact same thing. Can you tell me what would be the outcome?
Ketone.
Which one?
1, 2, 3, 4, 5. Two pentanone.
2-pentanone, 1, 2, 3, 4, 5, very good. And, right, it breaks right here.
And the primary.
The primary amine. You don't need to be able to name that yet because we haven't learned it. But do you guys agree?
Mm-hmm.
Please go ahead, take a stab at the mechanism. Think about what should be the first step, last step. Again, it's the exact opposite of the forward because these two are in equilibrium. The mechanisms are also in equilibrium. So, what should be the first step? Protonate what?
Nitrogen.
Sorry, protonate the what?
Nitrogen.
Nitrogen. Okay, then what? What's the nucleophile?
Water.
And where would water attack?
Carbon
Do you all agree? Exact opposite sequence of events. What you saw in the forward mechanism, this is exactly the opposite. Okay, so if that attacks, what does it create?
A good leaving group.
No, but the leaving group will take you back.
Oh, yeah, yeah.
It is a good leaving group, but then you're going in the reverse.
Yeah, yeah. I keep.
Okay.
Okay, so
What next?
the OH2 gets deprotonated.
And, okay, yeah, and? So you're right that this is going to give a proton. And who's going to take that proton? Somebody. This is going to get a proton from somewhere.
Mhm.
Isn't that right?
Yep.
Proton exchange. One is giving, the other is taking from somewhere.
Yeah.
So what does that do? Agreed?
Uh-huh.
What next?
Well, deprotonate.
But deprotonation
But we'll
will
just,
just
yeah,
take you
yeah,
back.
no, it'll take us back up.
Think forward. We need to go in this direction.
Leaving.
There's a leaving group. Exactly. That's a great leaving group exactly for the same reason
Oh,
why
that's where it
H2O is a
breaks.
great leaving group. Because you're going to create a neutral, a weak base.
Mm-hmm.
That's a good leaving group. Okay, so what does that create? A carbocation. A carbocation that is resonated, resonance stabilized. Exactly, and the amine, and the primary amine got kicked out, and so we have that now.
Uh-huh.
And the resonance stabilized carbocation, what does that guy need to do? Anyone? What does this need to do? Doesn't it just need to deprotonate
Yes.
and become the ketone? So, the
And you
point.
could do either one, right? Or
Say
not?
again?
Either resonance you could do. Or...
Oh yes, yes, you can do it with either resonance. That's totally fine. The point is, two things I want to point out. A, the mechanism for this direction is exactly the opposite for the opposite direction, the sequence of events. B, it's the same mechanism as acetal. It's exactly the same thing over and over and over again. The only thing that changes is the nucleophile, so suddenly we have a different outcome. Do you all see that? Everybody. Okay. Please tell me what would be the product. The mechanism you can practice at home. Anybody?
Oh, it makes one. I can try.
It's not okay for you to just sit there and nod at each other. Go do it over there.
I'm
You're what?
I'm sort of stuck.
You're stuck?
Yeah.
What? Okay.
You all agree?
Yes.
Basically, it's that carbon-nitrogen double bond that is breaking where you're adding water. Can we draw it differently also? 1, 2, 3, 4, 5, which is nothing but 1, 2, 3. So same thing. You're just looking at it differently. Agreed?
Mm-hmm.
Everybody?
Essentially, what I'm getting is that you're cleaving that C double bond N, and on the N side, it's an amine.
Isn't that what we did?
On
when
the other
you're
side
hydrolyzing?
is a ketone. Yeah.
You're adding water across the C double bond N and then breaking that and creating the hydrolyzed product. Exactly.
Mhm.
So please do practice writing these mechanisms. Of course, they're all the same over and over again, but do write. But let's go to the next reaction, which is similar, yet a little bit different. This is called enamine. Guys, do you remember enol?
Yes.
What is enol?
Alcohol with C double bond a C double bond C
What does this imply?
alkene.
C double bond C alkene.
Yeah.
And what does that imply?
Alcohol.
So an enol is when you have C double bond C and OH attached to it, right?
Right.
And we learned how they are very unstable. Typically speaking, they tautomerize to the keto form, ketone or aldehyde. We've done that. So anyways, the point though is, any guesses what an enamine is?
C double bond C
And-
with an amine on it.
Exactly.
Yeah.
That's pretty much what it is. So an enamine is C double bond C ene with an amine on it, and whatever that is. That's an enamine. So aldehydes or ketones, ooh, I have to draw this a little bit differently because it's tiny, it's a bit different. Aldehydes or ketones that have at least one alpha hydrogen. This is, excuse me, yes. So as long as there is one hydrogen on the alpha position to the C double bond O, next to the C double bond O, reacts with secondary amines, not primary, but secondary amines. In presence of an acid catalyst. Also loses water. It is a dehydration reaction, but intramolecular, not inter. But the point is, what's the product? So the water goes from here. Of course, this H, of course, this O.
And one of the H's on the alpha carbon.
Exactly. The water comes out H2O. From the alpha carbon loses one of the hydrogens as proton in the mechanism which we write. But what's the product? Guesses?
The bond between the C and the H being removed from a double bond.
Okay, so this becomes a double bond?
Yes.
Okay, so
And then the carbon will be single bonded with the nitrogen.
exactly, and whatever is on the nitrogen already. That's an enamine. Enamines are very common in organic syntheses for certain reasons, which we haven't learned
Enamines
yet.
are stable.
Yeah,
The compared to
absolutely.
enol.
Absolutely, unless you do something with them, yeah, absolutely. There's not, I mean, oh, you mean compared to enols?
Mhm.
Oh, yes, absolutely. Okay, so let's look at a couple of examples and write at least a mechanism at least once, and then we go to the next one. So let's say we have cyclohexanone reacting with diethylamine, which is a secondary amine. What is the product?
Is it always just gonna be with a second?
This one is for secondary, yes.
The sp2 carbon, oh, you're saying you're right.
So,
Are we writing it?
okay, don't talk, just do. One of, go ahead. What were you saying, sp2 carbon what?
Yeah, I'd say, because as make a double bond, you sp2,
Oh, I see.
they don't see no bond to nitrogen.
Yeah, okay, you mean the alpha carbon becomes sp2, yes. So you were asking, about the secondary, right?
Yeah,
This
always,
has to be secondary.
always has
Yes,
to.
for this one. Primary creates imines, which we saw earlier.
Oh, yeah.
Secondary creates enamines.
Yeah.
Tertiary can't do anything because they don't have a hydrogen on them. Do you all agree?
Mm-hmm.
Yes? Let's write a mechanism. Please, you will tell me. You shall tell me. What will be the first step?
Well, protonate.
Where?
Radial.
Okay.
Oxygen.
Next.
The nitrogen is gonna attack the carbon.
The NET2.
ET2, right?
Yeah, ET2NH.
Attacks where?
Carbon monoxide?
Because that's a nucleophile, attacks the electrophile. Agreed?
Yes.
Okay. What next?
Well, what do we get? Let's see.
Do a whole thing where you take one proton from the nitrogen moves to oxygen.
Proton exchange.
Yeah.
This loses a proton,
Yeah.
that takes a proton. Okay. Then what?
Take out the water.
Create a carbon.
Excuse me. Kick out the water,
Mhm.
create the more resonance stabilized carbocation. Agreed?
Resonance stabilized.
Okay, next what?
Um,
This is where the difference is.
remove one of the alpha hydrogens.
Because there's no hydrogen left here for anything to happen here, unlike primary amines. So therefore, the choice is one of the alpha hydrogens.
Oh.
That's why, because there is no hydrogen here
Oh.
anymore. Till now, everything is exactly the same. Okay, remove the alpha position loses a proton and, oh,
Creates a double.
creates a
The double bond.
double bond.
Okay. Oh.
Exactly. Creates a double bond, giving us enamine instead of amine. Everything else is exactly the same. Same steps. Do you all see that? Everybody okay? Make sense? Okay. No mechanisms again. You can practice at home. Just give me the other stuff. So.
Linda,
Yeah.
for that second one, you're not saying that the first one is going. is
Oh,
greater than
shoot, yeah, okay, yeah, thank you. No, I wasn't,
the- Okay, I'm just making sure. Getting confused.
yeah, thank you. Wow, we have 2 recordings going on today?
I just wanna make sure for Jane that,
Ah,
Dude, the video is super helpful. Thank you, Mara.
oh, good, I'm glad.
Is it just anything?
Just in case one
what do you
fails.
think? In the language of Ochem, what does that mean? Oh, why are you looking at her?
Oh, is it just?
What does this mean?
Oh. Oh.
Same thing, right? So do you guys actually watch the videos?
I do, that's the only way I can.
Just you? Just you?
I,
watch?
no, but some, not everybody.
So you guys like
Sometimes.
speed it up and speed it fast forward till you, because there's so much empty space.
I go back like 20 times to this,
Ah, oh my
till I
goodness.
understand.
That's a lot.
Transcripts you can search up too.
Oh, that's true. Yeah, yeah. If you know what you're looking for, you can just search up on it.
Ow.
But yeah, then you can skip the,
Yeah, exactly.
or pause it. Or... Well, that's what, no, we didn't have videos with you, we had them with Mark.
What? Yeah.
Videos, not with you. No, you never did videos.
For what?
For classes in Canada.
140 I do, but I don't know how many people watch.
Oh, yeah, you
I
did.
mean, out of 75, 15 come to class. I'm like, what? And then maybe 5 will
No, I
watch a
remember,
video.
I did, yeah. Mhm.
Yeah, I don't think a lot of people do.
Oh, because we had to be in lecture in order for you to send us the video, right?
No, the videos are there.
Oh, really?
I didn't have any, I don't require attendance. You wanna come, come. Don't wanna come, okay, have a great day.
Oh, okay.
Because,
I'm not remembering any.
but, so here's the thing. Sorry, what?
It's fine. Well, yeah, I think it was. It's alright.
The age, where do you, is,
Is there someone?
shouldn't the age, oh wait.
Does it matter
Wait,
which
does it matter?
alpha hydrogen you
Near
Why
the,
not draw the other one and then we can answer, does it matter which alpha hydrogen it
it
goes?
should be the,
Can we draw the other one?
by the end.
Because there are two different alphas, right?
Yes.
So what would the other one look like?
No.
Okay, yeah.
Oh, it is?
Yeah, now, what? Yes, why? Why not?
I'm confused.
No, you're good. You're good.
I'm confused myself.
There's an alpha here which is giving us this product.
Oh, I was.
There's also hydrogen here, right? And that's also alpha, so good. So the question, does it matter? Is one better than the other? What do you guys think?
No.
Oh no, look carefully. Please think before just
What's the
choose.
ability of alkenes?
Exactly. Isn't one alkene more stable than the other?
Yeah.
So should there be a major product and a minor product?
Yeah.
Yes. So does it matter which alpha proton goes?
Yeah.
Yes. The one that creates the more stable double bond. Absolutely. Totally agree.
There's also a third spot.
Oh really? Where?
Well, if you went to the opposite side,
It's the alpha of this guy. Those are the only two things. What do you mean opposite of where? Dash, come on, what are you thinking?
I was thinking in nitrogen.
But it's the alpha of the C double bond O, period.
Mhm.
Alpha hydrogen from C double bond O only.
Oh.
Do you all agree? Okay, cool. Again, please do practice writing mechanisms. By the way, let's go back to that equation right there. This is the forward direction. So what can you say about reverse? Is that possible? If so, what will you use?
H2O,
Just H2O?
dilute acid.
Because you do need that catalyst still, right? You do need H plus as a catalyst, and then water is a reactant. So it's exactly the same way, just like imines can be hydrolyzed, similarly enamines can also be hydrolyzed back into the parent aldehyde or a ketone. So please go ahead, tell me.
Are we reversing?
Yeah, we are reversing it, yeah.
Yep, we're reversing it. Turning the enamine back to ketone.
No, sorry.
Wait, hold on, what are you talking about?
I just drew it really small.
No, I've lost the carbon completely.
Where is your carbanion carbon? Where's your yeah,
There you go.
exactly. And then what's the amine?
Oh,
Not sure.
how do I draw that?
No, it's a product, so don't show in the arrow. That's a
Oh,
product,
oh,
right?
yeah,
So
yeah, yeah.
plus that, because the reaction is this way. So once again, where are the bonds that are breaking? Where is water going? Parts of water going. Bonds breaking right here. That's the bond that was formed, right?
Yeah.
One H is going here, one H is going here, O is going here. Isn't that right?
Mhm.
Everybody gives us those products.
Oh, I
Just
was.
the opposite. This is not imine, this is enamine, which means that's your alpha carbon. So if you're doing the same here, get creative. What is the product? Anybody?
Two, three.
Not quite.
No, no.
Yeah. Because if your connections, your bond connections are off. Anybody else? This is a tricky one. This is definitely a tricky one. Remember, we are adding water.
There's like 13
Our
of them.
byproduct would be NHCH3.
Yeah.
What did you say?
I just can't see it.
Oh.
She just said it was wrong. You think I'm right?
Okay, you got till there, but do you think that's done? What do you have left after this point? A good first step. What is that now? You write that is aldehyde on this side. This part is aldehyde.
Okay.
What about that side? What is that? It's an enamine. Enamine. Can't it also hydrolyze?
Oh.
Oh,
You're making up your
oh.
own
What?
So this one is a tricky one. It's a creative way of doing this reaction, which is not
So-
exactly like what you see.
Do you cut it again?
But the idea is the
I
same.
was gonna say, is the nitrogen attached? Or
To
is it,
what?
like, separate? Like, will I get separate products with mine?
You tell me.
Oh,
Is it an enamine? Is
Yeah.
it an enamine?
Oh, help me out.
Yeah.
You're adding condenses
I
in
think-
water.
Yes. Why not? We don't count water molecules, we just dump, right?
Yeah.
It goes wherever it needs to go and does whatever it needs to do. We don't have the choice. I do feel you have too many carbons though, or maybe not. Yeah, I think you have one. Oh, no, you don't. I'm so sorry. I'm miscounting.
Yeah.
And then
Yeah.
what was the
And then
nitrogen
what
take
happens
out?
to the nitrogen then?
I thought it had to have two.
No, it'd just be.
There you go. But you write so big that you take up all of my board space.
Yeah.
The four
Space,
board.
but I don't know, can you guys read what this says? Are you able to read this? Oh, really? Oh, God, you guys have really good eyesight.
I have good
You
glasses.
can,
I have
Vincent?
good glasses.
But you're absolutely right. There are two enamines here. This is an enamine. Do you see that? Enamine. Agreed? But this is also an enamine. Enamine. So this can hydrolyze twice. In both cases, hydrogens will go. Where will the hydrogens go? Hydrogen, hydrogen, oxygen the first time, right? But then hydrogen, hydrogen, oxygen. So you're breaking this, end up with a dialdehyde and a amine right there. Absolutely. Do you guys see that? Yes? Cool. Okay, that's enamine formation. Let's go to the next reaction, that's cyanohydrin formation. Again, everything is exactly the same pattern, mechanisms, blah, blah, blah. So, what is a cyanohydrin? It's a fancy name for something you get
Cyan.
when an aldehyde or a ketone is reacted with HCN, hydrocyanic acid. Same thing. Now, you've written this mechanism like so many times, you can probably tell me where will the CN go? Oh, come on, guys.
Push the R.
That's not okay. It's an acid. So where will the CN go?
In place of the oxygen.
In place of the oxygen?
Well, it will attack the
To the
carbon.
carbon. Where will the proton go?
Oxygen.
So what's the product?
Alcohol. You see it.
Not an alcohol, cyanohydrin. So we are basically adding HCN across the pi bond, just like we added water, just like we added alcohol, just like we added amines and blah, blah, blah. Now this time we are adding HCN across the pi bond, and here is your HCN. This is called a cyanohydrin. Now, just FYI guys, HCN is again not something we keep. HCN is generally created in situ. When you're doing a reaction, you're really creating it as it's doing its stuff. So we don't actually use that. We use a combination of potassium cyanide with an acid. Potassium cyanide with acid creates HCN and then the reaction. So, do we have to write a mechanism? Because we've written it 1,000 times, I feel like already. What's going to be the first step, anybody?
Oxygen gets protonated.
And then?
Nucleophile attacks the carbon.
Got it. Okay, so then please make sure you know how to do it. Let's do some examples. Now, by the way, what's the purpose of the nitrile group, the cyano group, whatever you want to call it, is actually a very useful group synthetically speaking. The CN group or the nitrile group, this guy right here. So we can either hydrolyze the nitrile, so this carbon right here, and we'll look at the detailed mechanism of that step next chapter, I think, but this becomes a carboxylic acid. And of course ammonium and all, but who cares? So it's this carbon is that one right here. We can also reduce the nitrile using La, only La. Sodium borohydride doesn't work for it, it's La, in which case the CN group becomes a primary amine. So that becomes primary amine. So that's really useful in terms of synthesis to be able to, get to other functional groups from there. Okay, so let's try this. Fast, please.
heat a little bit.
Okay, can someone tell me what is the outcome of the first step? Let's do this quickly. It would be great if we can finish this chapter today. What's going to be the first step? Say that again?
I don't know what it's called. It's
Cyanohydrin forms?
Okay, it makes a cyanohydrin because, agreed?
Mhm.
Okay, what next? LAH and then water. So what is happening to the cyano group with the
It
reducing
becomes a primary amine.
CH2 and H2. So the carbon becomes CH2 and the nitrogen becomes NH2. You're reducing it completely, so agreed?
Yep.
Okay. Next one.
First up, it becomes a primary alcohol.
Okay, first step becomes a primary alcohol. Then
KCN, cyanohydrin.
no, not yet. What about step 3?
Oh, PCC turns it into a ketone.
No,
No,
it's a primary alcohol.
Oh, it's an aldehyde.
Aldehyde, exactly. Secondary alcohols will become ketones, but yep, aldehyde. Okay, step 4
Cyanohydrin.
becomes a cyanohydrin. And step 5.
Carboxylic,
Which part is becoming carboxylic acid?
the cyano group.
Right, exactly. Everything else stays as is. Agreed, everybody? Okay, I need you to convert benzene into that product shown in 3 steps. 3 steps. Okay, I see. Okay, the word steps might be confusing. Okay, 3 reactions, let's put it that way. Yeah, not steps. Anybody? No one?
Like,
Do
could
you
we use
notice
a?
this,
Could we use a?
right?
Mhm.
CH2.
Yeah.
Where could that have come from?
from
A cyanohydrin.
That's the cyano group, right?
Mm-hmm.
So everything, we're going backwards. That's a cyanohydrin. Where would that come from?
A cyanohydrin, KCN.
Fine, but what's the you're right, you need KCNH, blah, 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 but what's the reactant?
Ketone.
Ketone in this case. Absolutely. Do you all agree? Where does that come from?
An alcohol.
Ooh, not in this, we want it in 3 reactions.
Oh,
Besides, how would you get the alcohol there? It adds
An
to many
acyl
steps.
chloride?
Can we convert benzene into that?
An acyl chloride?
Exactly. Friedel-Crafts acylation, you got it. Okay, you can finish it now that you know what to do. You can add the reagents and so on and so forth. Let's go to the next reaction, which is actually a very interesting reaction, because in a way it's opposite of ozonolysis. If you think about ozonolysis, how it breaks an alkene into two parts, right? This one kind of creates an alkene from two parts. So this reaction is called Wittig reaction. You will see this reaction being used in syntheses quite a lot. It's a very useful reaction.
This is number 10.
Yes, thank you. Thank you. Okay. So what is Wittig reaction? Wittig reaction is a reaction between aldehydes and ketones. So aldehydes and ketones, or ketones I should say, not and, or ketones, react with something called, I'll tell you what it's called in a second, but on prime. Something that has that structure. This is called, can you pronounce this word for me?
Yield.
No, it's Yllid. Yeah, that. I always have trouble pronouncing this word. This is a phosphorus Yllid because there's a phosphorus in it. It's interesting because it takes this portion and connects it to this portion, and we're not getting into the mechanism. There's a mechanism, the book might actually have it, we're not going into it. So it's this piece that connects to that piece. Can you tell me what the product will be? This piece, that piece connected together. What's the product?
Could be C.
An alkene. An alkene. So it's in a way opposite of ozonolysis, where you are snapping these two pieces together, making an alkene. What's the byproduct? The byproduct is triphenyl phosphine, which is actually pretty toxic, but who cares?
Just don't get me wrong.
Now, what? No, we're not going to. We don't have the capacity to deal with that level of
Toxic.
exposure, yeah. But if you were in a research lab, it's not a big deal because you have the proper equipment to handle it. Now, where does the Yllid come from? That's the important part. The Yllid actually comes from alkyl halide. It comes from, how do I show this? I shouldn't have done that. Okay. The Yllid comes from, let me start here. An alkyl halide. It can be primary or secondary. Can't be tertiary, but it can be primary or secondary because we do need one hydrogen. And in the first step, it's just an SN2 reaction. It's really an SN2 reaction where that's the nucleophile from the phosphorus. Nucleophile attacks the electrophile, kicks out the leaving group. It's actually an SN2 mechanism. And it creates agreed? I'm missing one thing. Can someone tell me what is it that I'm missing? What am I missing in that structure? This is a question I always ask for one specific purpose. Word starts with the letter C and ends with the letter E. The second letter is H. You're gonna make me spell it out. Charge.
A charge. A plus
Where?
charge.
What? Charge.
Why?
Without charges, your structures are wrong, especially middle of third quarter.
Oh,
Where
because that's an H, right? Or not?
Where what?
Yeah, in the C is a minus.
But the C has 4 bonds. Why should it have a charge?
Isn't that like a hydrogen?
But it has a charge. Can't carbons have
Oh,
hydrogens on
never
them?
mind.
Oh, the phosphorus?
What?
The phosphorus?
What charge?
A negative? A positive.
Positive. That gave electrons, oops, sorry, not high, kicked out the leaving group. Did it get any electrons?
It gave electrons.
Positive. Exactly. You gotta keep track of your charges.
Oh.
Everybody okay?
Yes.
That's the first step. And then this guy is reacted with a very strong base that you've seen before, N-butyl lithium. A very strong base. What does a base do?
It accepts a proton.
And where is the proton going to come from here?
The,
That's this proton.
yeah.
That's why we need a hydrogen there. Because the base takes the proton, which creates that double bond. The yelid. So the yelid is created in 2 steps, SN1 followed by an acid-base reaction. Yelid, once you get the yelid, it reacts with an aldehyde ketone to produce an alkene. This reaction is called the Wittig reaction. Now there are wonderful variations of this reaction that have been developed through research. Of course, we are only going to look at the standard, very standard Wittig reaction. Now, do remember, can alkenes have stereochemistry?
Yes.
What kind of stereochemistry can alkenes have?
Easy.
Good.
Easy.
Z, which is more stable, generally speaking. Which isomer is more stable, E or Z? In general.
E?
Why? Because that's trans. Generally speaking, you know this, trans is more stable than cis is, which means E is, you will get E plus and Z products. If that matters, you'll get both. But the expectation is that this would be the major product, just because the E alkene is more stable than the Z alkene. Sounds okay, everybody? Okay, let's try this out. No mechanisms needed here, just the reaction. So we are starting with an alkyl halide, and I'm going to react it with triphenylphosphine followed by butyl lithium. What will that create? And once you got this, what will be the product? No, not tomorrow. That wouldn't be fair.
No.
Say again?
Nothing.
You're like, you want me to?
No.
It's anyways too late because I've already written it, but yeah, I mean, that wouldn't be fair too.
Ricky said he wrote the exam last night that we took this morning.
Ricky is young. He's resourceful. So in a sense, if you think about it, I want to do that. In a sense, just to highlight, in a sense, what's going on is you're taking this portion and you're taking this portion and connecting them to each other. Isn't that right?
Yeah.
So if you can find that shortcut to figure out what the product should be quickly, then yeah, absolutely. Hey, Pat, you have the textbook open, right? May I take a look at what section are you on? Okay.
I just light up. If it's not heat, then just light up, I tell myself.
Nobody for this one? Oh.
Sorry for this piece, but
Yeah, absolutely, absolutely. It is, yeah. Save time.
Yeah.
Okay.
And then here, you have
You lost a carving.
me?
Yeah.
I did. I did. Thank you.
Mm-hmm.
Yes, wait. And then I think from here, I think.
So are there two products, with like how you put them together?
Yeah.
Okay.
Exactly.
You're right.
Yeah, why is that benzene?
Oh, I see.
Stop doing that.
Yeah. Okay. Do you agree?
Yeah.
The only one, your answer is absolutely correct. And I know you weren't trying to do that, it was just way too high.
Yeah.
That's not linear, right?
Yeah.
This bond is at an angle because it's sp2 hybridized.
Mm-hmm.
Perfect. Do you all agree, everybody?
I think
Yes.
I'm woolly when
BU,
B
BULI?
and you.
Uh-huh.
Like when that comes in, what happens?
Takes the proton and makes the double bond between carbon and phosphorus.
So these makes that one over there?
Yes, exactly.
Oh, okay, got it. Okay, so.
Exactly, yeah.
So do you go next to me?
No, so you're starting from here, you're making that, making the yelid, which then reacts with these to create the carbon.
Oh.
Does that make sense? So like how Dash is saying, first you got the bromine and trioxide, and then the triphenyl phosphine, step 2 followed by 3, 2 and 3 makes that. 2 and then 3 makes this. And then this reacts with the aldehyde or ketone, this portion combines with that portion to make the proton.
Okay.
This is Wittig's reaction. Again, no mechanism needed. I don't know if the book has one mechanism, but we don't need to. I'm already over time. We have one other tiny reaction left for this chapter to cover. So we will finish this chapter on Wednesday and start the next one, that is carboxylic acids and derivatives, I think, something like that. So yes, we'll start that next class. Huh?
Is it derivative like calculus?
No.
Okay.
No. There's a reason I'm not go engineering path. There's a reason I didn't go engineering path, that's calculus, because it kicked my butt. And there's a reason I didn't go in medicine path, because biology, oh come on. So this dissections and all, it's like, nope, I'm not.
Calculus or biology?
No, the organic.
So,
teacher-
organic chemistry is perfect.
Yeah, the
So-
organic chemistry teacher online on YouTube.
Yeah, said the same thing?
No, they,
Oh.
he had videos about like, stuff, about like,
Really?
but you can teach it all steps.
Oh, yeah,
It's
that's
called
right.
the organic tutor, but it's
But
really
he
all
teaches
steps.
us. Is he good?
Oh, yeah.
What's his name? Oh, okay. Have you shared the link with everybody else?
He's a pretty common guy. Like,
Okay.
look at him.
YouTube, you said?
Yeah,
What guy?
Yeah,
organic chemistry tutor.
tutor.
Oh, yeah.
Who we watch from a lot.